All right, there we go. So yeah, today I'm going to talk to you about a project which started in my research lab here at Queen Mary in the Center for Digital Music in 2013 and 14, and has subsequently basically become an open source community platform that has spun out of the university and has sort of acquired a life of its own. So just a little bit of background about where I'm coming from. My own background is as an electronic engineer and a composer, and I lead a research team that works on digital musical instruments and interactive systems for music. Now, this talk is not going to be anything specific about music, because as you'll see, the tool that we have created in Bela addresses a fairly general purpose set of applications surrounding real-time audio, and I'll talk about some of the performance issues and some of the development considerations that I think will have a fairly broad relevance. So just to talk about what Bela is. So Bela is an embedded platform for processing audio and sensor data in real time with low latency and high performance. So in essence, it's a single board computer running a custom operating system, real-time Linux, and also custom hardware for doing audio and sensor sampling and analog digital and then an audio codecs. And one of the signature features of Bela is that it can achieve a throughput, round-trip latency of less than 1 millisecond end-to-end for audio, which is about 3 to 5 times better than even a high-end laptop will typically achieve. Another thing that Bela introduces is a new approach to processing sensor data, where in contrast to some of the approaches that are typically found in the kind of maker community with boards like Arduino, where maybe you sample sensor data occasionally, you take an analog reading maybe 500, 1,000 times per second, let's say, sensor data can be treated as essentially an audio signal in itself, or an audio rate signal. And what this allows is a lot of the same kinds of techniques and algorithms that you might use for audio can be applied equally well to other forms of sensor data. Finally, Bela is an open source platform. It's open hardware, it's open software, and it's something that we've gotten out there to the community, and it's being used for a wide variety of applications in research, in industry, amongst artists and makers. Now, I want to maybe start with just a little bit of theory that may be familiar to a number of people here, but in talking about Bela, we often talk about its low latency performance. So what are we talking about here? Well, latency is essentially delay. It's the delay between the input and the output of a system, and it's a fundamental property of digital signal processing systems. So in this case, for instance, if we had sensor data coming in, and some sort of audio event that was reacting to it, the latency is defined essentially as the delay between the reception of that event and the audio that comes out. Simple enough. Now, there's a reasonable question, which is, to what extent does delay really matter? Does delay really matter? Does latency matter? And it turns out that in a musical context, the answer is yes, absolutely, it matters intensely what the latency is. And this is obvious to a certain extent, that if your audio system has an audible delay to it, then that's not going to be acceptable in a lot of situations. But it also turns out that in digital musical interaction context, that even delays that are too small to consciously perceive nonetheless degrade the perceived quality of an interactive system. And the general guideline that's often offered is around 10 milliseconds from input to output is the upper limit, and that also needs to be very consistent without a lot of variation in it from event to event. Now, we have actually done some studies with professional percussionists where we verified this, that in fact 10 milliseconds of latency seems to be okay if it's consistent. Less than that is obviously ideal. More than 10 milliseconds becomes a problem. Now, what's interesting is that actually very few systems for building digital musical instruments, or general real-time audio processing systems, meet this latency threshold. And that's especially true when we talk not just about audio input to audio output, but systems that take in other sorts of triggers or events and generate audio in response to that. Meeting this specification is actually not as easy as it seems, even in 2019. Here's some of the reasons why that's the case. So if you encounter an audio processing system, you'll have a number of sources of latency in the round-trip audio path. One of them is intrinsic to the converters themselves. So typical audio converters use sigma delta conversion. This is essentially a mathematical process which has some really useful properties in terms of allowing very high performance, high bit depth conversion of signals with relatively inexpensive hardware. The trade-off for a sigma delta converter is that there's typically a short FIR digital filter inside the converter chip itself, which introduces a certain amount of latency, which is absolutely intrinsic to the part. Doesn't matter what your software and operating system are doing. So that might be up to about 1 millisecond total, depending on the chip you're using. One of the big sources of latency that comes in a digital audio processing system has to do with buffering in the operating system. And this usually has to do with the fact that in a complex multi-user OS, you typically have a lot of different processes running, and the hardware is not able to respond immediately to each audio sample as it comes in, so you have to parcel them together into blocks, and the larger the block size, the larger the latency that you'll get. And then, of course, whatever audio code that you write will also potentially introduce its own mathematical latency. Now, to emphasize something here, we are not talking about something that has to do with how powerful your CPU is. These things all apply exactly the same, whether you have a tiny microcontroller or a massive 16-core top-end desktop processor these days. And it has to do, like for instance, in the audio code, if you're working with block-based processes, FFTs, this sort of thing, as you may be familiar with, that naturally imposes a certain latency before the block can be assembled. Doesn't matter how fast your hardware is. And here's a little illustration of what typically happens in a real-time audio processing system. What you do is you fill up a block of samples. Now, having filled up one block of samples, this might happen inside the operating system somewhere, that'll get passed across to your audio processing code. You're expected to do any processing while that block is available to you, and to produce the result, which then gets played at the next block. So what that means is that at any given time, we will be reading one block of samples in from the input hardware, processing the one right before that, and playing the output of the one before that. Net result is that in a real-time context, your total round-trip audio latency is always twice your buffer size. It takes 2 buffer lengths for something to make its way input and output, even if you don't do anything with it in the meantime. So the larger the buffer size, then the larger the latency. So for example, if you were working with a block size of 512 samples, this being a common value that you might encounter on a desktop machine, that means that you have 1,024 samples of total latency. If your audio sample rate is 44,100 samples per second, you can work this out, and that's about 23 milliseconds round trip. Again, already greater than our 10 millisecond guideline threshold. So this is where the problems come from. Now, the problems get a little bit more complex when we're talking about systems that are not dealing only with audio, but also with other kinds of sensor data and events. If we're sampling some sort of signal, for example, let's suppose that we have an Arduino board or something similar, which is hooked up to some sensors. The Arduino is sampling the sensors. Whenever it gets a sensor reading, it sends it across the USB to a computer which is running some kind of audio processing software. Well, there's going to be a latency associated with the sampling of the sensors themselves. That depends on the sample rate. There's going to be latency associated with communicating between the Arduino and the computer. Some of that actually at a hardware level. The USB protocol itself sends packets every 1 millisecond if you're working with full-speed USB. And this can very easily translate to a few extra milliseconds of latency just on an electrical protocol level. The real problems, though, start once you end up inside the operating system drivers. What happens here is that a lot of the drivers you'll encounter on your machines are not optimized for latency. They're optimized for data integrity. Like, for example, a USB serial driver wants to be very sure that it doesn't lose any bytes of data, but there's no guarantee on how long it might take for a particular byte to actually reach the application code. So it becomes very unpredictable, very jittery. And then, of course, we still have all of the audio processing latency talked about in the previous slide. So this is some of the sort of lay of the land in terms of some of the problems that we encounter. Another problem that we will encounter is not just a static delay, but that the delay can vary randomly. This is called the jitter of the system. And just to illustrate where this might come from, suppose that you had a real-time system that was processing audio in blocks of samples, and suppose that there were some events that were coming in. You know, we receive a signal from some sensor, and it happens at any time. Could happen at the beginning of a block, could happen in the middle of a block, could happen in the end of the block. Typically speaking, the sensor data is not synchronized with the audio. It's not coming in on the same clock, it's not coming in the same thread in the computer. And so oftentimes what happens is that the kind of best that you can really do is react to that trigger at the beginning of the next block of audio. And so what ends up happening then is you can see that the delay, the latency between receiving a trigger and reacting to the trigger varies one trigger to the next. It's not consistent. And basically the larger the block size that you have for your audio, the more jitter that you're going to receive. Here's actually a practical measurement of this. This is a histogram plot of essentially 1,000 triggers that were sent to an Arduino board into a computer running MaxMSP to generate sound, and you can see that they vary in what the latency is. So 14 milliseconds seems to be our kind of mode there, but we see some at 11, some at 8, some at 17. Basically, we see different latencies kind of in jitter at intervals of the audio block size because of this effect we talked about. Right. So this is the background, and this kind of performance of real-time systems issue was what inspired us to make Bela. And just to talk a little bit then about what it does and some things that we might consider for developing real-time systems for audio and sensor processing. Bela started out as a project about building digital musical instruments. Now, I know this is a fairly niche application area in a sense of building an instrument not only to make sound and music, but also an instrument that was designed to be modified and hacked by the performer in kind of unpredictable ways. There's a whole backstory to this which is not important for today. But suffice it to say that having built one particular instrument, what we discovered was gradually over a period of about 2 years, found that, hey, the same hardware and the same code that was useful for the D-Box is also useful for this other thing that we're doing in the lab, and it's also useful for this research project, and it's useful for this class that we're teaching. And then, kind of gradually we started to find other collaborators who had similar sets of problems and requirements, and it sort of organically grew from one very specific thing up to the point where it was something that had quite a community around it. And in 2016 then, to really try to turbocharge this, we took it to Kickstarter. Now, Kickstarter, as I'm sure most people are familiar with, it's a crowdfunding platform for basically launching new ideas of various sorts. It's very good for kind of, number one, getting the funding that you need to be able to build a lot of things, but it's also a really good way to raise attention and publicity around a new idea. So we launched Bela on Kickstarter in 2016, and it seemed to touch a nerve in some way because we actually ended up with a much better reception than we even expected. And essentially since then, we've spun this out and have continued to support it and develop it as an open source platform. So this is what Bela is. It's based on the BeagleBone Black single board computer, which is, I guess about similar to Raspberry Pi 2, let's say, in its processing capability. A 1 gigahertz Cortex A8 processor, neon vector floating point, and this thing called a PRU microcontroller, which we'll come back to because it's actually a really interesting architectural detail of the BeagleBone that we use. We have equipped it with a add-on board that supplies stereo audio, I/O, 8 channels each of analog input and output, those being 16-bit, and a few extra things, speaker amps, and of course connection to other more complex buses, whether that's I2C or USB or Ethernet, what have you. Some of the kind of special sauce, I guess, for Bela is not just in the hardware, but it's actually in the software architecture, where we're running something called ZenMI Linux. ZenMI is a set of real-time extensions to the Linux kernel, and probably the easiest way to think about this is as if all of Linux was running in a virtual machine on top of a very kind of lightweight, high-performance real-time OS. What ZenMI lets you do is it lets you write code that can interrupt anything on the board in a deterministic timing guarantee sort of way, including the Linux kernel itself. So you can write code with the secure in the knowledge that you are giving basically the highest priority thing on the board, almost as if you're running bare metal on a microcontroller. And what this lets us do is eliminate a lot of the uncertainty in the operating system and get ourselves down to audio buffer sizes that are as low as 2 samples, which is much smaller than you would achieve in any laptop or mobile phone sort of context. And this essentially takes away one of the biggest components of latency. And also there's an alignment between audio and sensor data that I'll talk about in a minute that essentially effectively eliminates this jitter problem in terms of reacting to sensor events. Right, so here's a little bit about the hardware architecture. We have various chips on the Bela Cape, which is our hardware accessory board. That includes an audio codec, Sigma Delta codec, a 16-bit DAC, a 16-bit ADC, using various high-speed serial buses, I2S, which is the audio, a serial bus specifically for audio, SPI, which is a generic high-speed synchronous serial bus. And the question that we encountered was essentially, how do you write a driver for this? How do you actually get the machine to talk to this hardware? And the first thing that came up is that you actually cannot use the Linux kernel to talk to any of this hardware because the kernel is too slow. Or more specifically, because the kernel might be busy doing other things at any given moment and you can't guarantee a particular reaction time when it's time to get a new sample of audio, or when it's time to query the ADC that's connected to some other sort of device. We actually have to go to a lower level still to be sure that we can have the timing performance that we need. And the way that works is like this. Instead of using a typical Linux driver for this hardware, we're going to use this PRU, which stands for Programmable Real-Time Unit. The BeagleBone, the chip that's used in the BeagleBone, is a system-on-chip that has, on the same die, this ARM Cortex-A8 CPU. And also, on the same silicon there, it has 2 of these PRUs. And what they are is they're basically microcontrollers with a very timing precise instruction set. Every instruction on the PRU takes 5 nanoseconds, basically full stop. And maybe there's a couple that take a deterministic 10 or 15 nanoseconds. But the point is, you can basically time out exactly how long a particular sequence of instructions will take to run, which is not true of most modern processors, where there's a lot of uncertainty because of optimizations that they use. So what we did is we used the PRU essentially as our kind of data gathering hub. The PRU does all of the interfacing with these high-speed serial buses, gathers data from the audio codecs, gathers, sends data to and from the ADCs and DACs, and it parcels it all up into these, basically into these packets that are shared across shared memory to the CPU, which actually does the heavy lifting in terms of whatever DSP code that you would like to run on it. And in doing this, basically what we can do is achieve a more deterministic, lower latency latency to data coming in and out. So yeah, we don't need to get tremendously into this detail, but suffice it to say that having the PRU share memory with the main processor is a very useful architectural feature of the BeagleBone, and the reason that we've used that rather than, for example, the Raspberry Pi to make Bela. Here's a useful principle for real-time DSP in general and audio in specific is, of course, to consider the worst case performance. That if we're talking about a live musical performance environment, then glitches, dropouts, underruns are really not acceptable. Clicks and pops in the audio that comes out is really distracting. And so what that means is that in this context, meeting 99% of your deadlines is just really not good enough. You need to meet 100.0% of your deadlines, or your real-time system is not performing according to spec. And so what this means then is that we have to be able to have very kind of guaranteed timing performance. And here's the reason that this might be difficult. Let's suppose that you're on a Linux system, you're running a number of different processes. P1 and P2 are different processes, user space processes that are running on your machine. You also have the kernel doing this and that. I don't know, maybe it's doing some sort of memory allocation, maybe it's doing a network operation, who knows. And then you have your audio process. And what happens is when the hardware pings you and says, I have a new buffer of audio available, you want your audio process to run to be able to do whatever you want with the data. Now, the thing is, it might take a little while. on a typical desktop OS because the kernel's busy doing something else. So yeah, I'll get to it eventually, and it might be a few milliseconds later before your code even gets to run at all. And you can't really guarantee this. So what Xenomai gets us is the ability to essentially interrupt anything that's going on the board whenever there's audio to be processed. So here, for instance, we have, if audio becomes available, I can run my Xenomai task, my real-time task, immediately at that moment, and put this, basically put the kernel on hold. And this is something that's called primary mode in Xenomai as opposed to secondary mode, which is all your normal priority stuff. Now, it might be reasonable to ask, essentially, why doesn't this wreck everything? How can you just interrupt what the kernel is doing and not essentially break your entire system? Because, it's in the middle of its own important stuff. And herein lies the beauty of the Xenomai approach, which is that because you're effectively running Linux in a virtual machine, the kernel never even knows it was paused. It just kind of gets put to the side and comes back exactly where you left off, very transparently. Now, that leads to probably the main constraint then of developing a system in a context like this is that basically nothing in your code is allowed to change the state of the rest of the kernel. And that in turn means that you're not allowed to have any system calls in your audio callback. So no allocating memory, no talking to the network, no accessing the file system. You can't do that in your audio thread. As long as you restrict yourself to that constraint, you can do an awful lot of things. I think, I don't want to take too much time here, but basically, the mechanics of going through this is all about what you need to do to avoid these underrun conditions where your code takes too long to run, and usually the typical response is just make your block size bigger so that you can handle more uncertainty. But that's exactly how you end up with these very long latencies, and in lots of applications that's really undesirable. So we'll skip across that, but just suffice to say that an interesting thing about Bela is that you can use almost 100% of the CPU on audio to the point that basically all the rest of Linux is completely starved of resources, but you don't notice a single underrun because it's guaranteed to be the highest priority thing on the board. So I'll skip across this. And the smaller you make your block sizes, the better your jitter performance can be, which is also desirable from a real-time perspective. But in fact, we can do a little bit better than that. And one of the things that we designed into Bela was that these other sensor streams, your analog inputs and outputs, your GPIOs, your digital inputs and outputs, are all sampled synchronously on a frame-by-frame basis with the audio clock. So that means that if you want to gather data from some arbitrary sensor, a distance sensor or a light sensor, you can actually align it down to about 25 microsecond precision to a very particular sample in time of audio. And this turns out to be useful and avoids a lot of kind of reconstruction and clock drift issues that might happen otherwise. So that, for instance, everything would be parceled together into these memory buffers, and it's all just available there for your code to look at. And then essentially, this also enables a sort of useful property where you can start to use the same kinds of techniques and tools that you would normally use for audio processing can be applied equally well to any continuous valued sensor data that you might get, because it's all been sampled in a very similar way. And we've built some various hardware to support this, to turn extra audio channels or extra analog channels into audio channels, to expand the available number of channels. There's a variety of approaches here. If this is something that you have a particular idea or application in mind, we've got a few other things that are kind of under development, so always happy to have conversations about these things. And one of the things that it enables that really has been an important research goal for me, kind of bringing this back full circle, is it's not just data processing for data processing's sake. It's about the nuance and it's about the subtlety that you can get when the things that you're measuring about the world are not just a few samples in time of a sort of high-level phenomenon, but actually the tiniest little details of how somebody interacts with a system, and that even sensor streams where you think it really should be fine to take this 50 times per second. At the point that you really crank it up and you have this very high bandwidth sensing, you can discover lots of detail in these signals that can be useful for all sorts of applications. So, bringing this around to a conclusion then, we're working essentially with 3 layers of real-time in our real-time context for Bela. One is our sort of soft real-time of Linux systems, where you need to do things approximately now, but if it's a little bit later, that's okay. Network, file system, USB, that sort of thing. Our audio processing and our sensor processing, which runs at a much tighter time scale to provide these latency guarantees. And then for our own architecture, we also had to go down to the kind of microsecond scale to be able to deal with these various high-speed serial buses and gather the data together in a very deterministic, coherent way. This is an example of some of the performance that comes out of that. You can see basically the lower bars are better, let's say. The smaller the bar, the shorter the latency. And against a kind of baseline of 10 milliseconds out here, you can see that all of the Bela settings are substantially shorter than that. And that also, the jitter between successive action to sound latencies is very small, 25 microseconds or less. And that compares to some of the other things that are out there for doing interactive systems with sensors and sound, where it's not uncommon to encounter latencies on the order of 20 milliseconds or more with significant jitter. So yeah, I guess with all that in mind, Bela's a maker platform. It's a thing that's out there. I'm not here necessarily just to promote this particular solution to all possible problems, but this is kind of a way that our research requirements led to something that was more generalizable and has effectively resulted in an approach to real-time signal processing that may have a set of applications across a number of different domains. I think I'm going to stop there and just leave you with, there's a website for more info. That's our Twitter handle. And if there's time, I can take a question or two.